This is Physical Chemistry, Part 1, Thermodynamics, Chapter 7, The Properties of Real Gases, Section 7.1, Real Gases and Ideal Gases. First, what are the differences? In an ideal gas, the atoms or molecules do not attract or repel each other. In an ideal gas, the size of individual atoms or molecules is zero. We are assuming the radius of every single atom is exactly zero. All collisions are elastic collisions between ideal gas atoms or molecules. That means before and after the collision, the total kinetic energy is conserved. In real gas, the atoms or molecules attract and repel each other. The size of individual atoms is non-zero. For example, in a helium gas, the radius of every single helium atom is non-zero. R is roughly 1.4 angstroms. And then we can use 4/3 times pi times r to the power of 3 to calculate the size of one helium atom. The size of 1 mole helium atoms is simply this 4/3 pi r to the power of 3 times the Avogadro constant. That will give us a good estimate of the parameter B in the Van der Waals equation. The collisions between real gas atoms or molecules are not elastic. The total kinetic energy is not conserved. Now let's look at this Van der Waals gas equation. Pressure is nRT over V minus Nb minus An squared over V squared. This part is the attraction part. A is the parameter that accounts for attraction. B is the parameter that accounts for the finite size of the atoms or molecules. B also represents the repulsion between the gas atoms or molecules. With a larger A, we have a lower pressure. With a larger B, we have a higher pressure. So if we look at this equation, we can divide top and bottom by n. Over here, we can divide the top and the bottom by n squared. And then P is equal to RT over molar volume minus B, minus A over molar volume squared. The advantage of doing this is now if you look at temperature and molar volume, they are both intensive properties. And pressure is also an intensive property. So if you look at this equation, none of these parameters or variables depends on the number of moles of the gas. Now let's look at the parameter A and B for some gases. If you look at A, which gas has the highest value of A? Water. Well, if you look at all these molecules, helium, hydrogen, argon, nitrogen, oxygen, CO2, water. Only water has a non-zero dipole moment. So it's not surprising that water has the largest parameter A because the attraction between two water molecules is greater than that of any other gases here. CO2 also has a fairly large A. CO2 has a zero dipole moment, but because CO2 has many electrons, many valence electrons, it's easier to change the distribution of the electrons. So it's a lot easier to create a non-zero instantaneous dipole moment when electrons move. For the same reason, the parameter A for argon is greater than the parameter A for helium. Now let's look at B. B is the size of the molecule or the repulsion between molecules. So which one has the largest B? Well, if we look at these gases, CO2 actually is indeed the largest molecule in size. Again, if you compare CO2 and H2O, you can see these oxygen atoms are bigger than hydrogen atoms. And if you compare CO2 with oxygen, well, in CO2, there's one additional atom. And also, if you compare argon with helium, well, both are atoms, and argon is bigger than helium. The last row is so-called boil temperature. It's just A over BR. Later you will see. At this boil temperature, the compression factor is equal to 1. And we have all those boil temperatures. Basically, it's just this A divided by this B and divided by R. Make sure that you pay attention to the units. Since we're using liter and bar, this R should be 0.083 bar liter per mole K.